Are you in the industrial space, possibly an engineer, a technician, or maybe somebody who just wants to better understand how a flow meter works? Well, you're in the right place. My name is Dan, and I'm gonna go through 5 primary flow meters that we see out there. Give me a few minutes and we're gonna dive into these 5 flow meters, and we're gonna help you understand a little bit more about how these meters work. First, we're gonna go with mag meters. Mag meters are designed to be used in conductive fluids. Conductive fluids are something like waters or acids. They're not oil-based products. Oil-based products might be your vegetable oil, diesel, petroleum. These are not conductive and generally not used for mag meters. Mag meters operate on a magnetic field and an electrical principle. And in order to properly measure, you need some sort of conductive fluid. So mag meters are a velocity measurement. So if you've got a cross-sectional area of a pipe, so pi r squared, that's how you determine the area, and you've got a known velocity, which is essentially what a mag meter is measuring, you've got a known volumetric flow rate. These are often a very accurate measurement. You've got something between 0.15% and 0.5% accuracy. Second thing we're gonna do is we're gonna go through Coriolis meters. Coriolis meters are using the Coriolis effect. If you've ever taken a hose and you let it wobble back and forth, you're holding it on 2 ports, and then you start flowing water through it, you'll see it start moving like a snake. This is called the Coriolis effect. And you've got sensors that are measuring how far those things are wobbling, how fast they're wobbling. All of this is gonna give you a direct measurement of mass flow. Mass flow is often used for chemical dosing when you're trying to do highly accurate measurements in a batch type formula. And sometimes Coriolis meters are used for custody transfer. Again, these are extremely accurate meters. By measurement of mass, you can go oftentimes down to 0.05% and then all the way up to 0.5%. You're measuring density with these, you're measuring temperature. These are often used as a multivariable measurement because of how much you can get out of them. However, beware, Coriolis meters are often a very expensive meter. So you could see dollar values up into hundreds of thousands of dollars depending on how big you're going to use. So not the economical approach, but definitely necessary in some applications. You know, if you're comparing it against a mag meter, these will measure the volume and the mass of a petroleum product or an oil-based product that the other mag meter did not. Third, we're going to go with the vortex meter. The vortex meter is often used in gas flows, liquid flows, and oftentimes steam flow. The most common place that I see them out there is in steam measurement. Vortex meters are used similar to a mag meter. They're also a velocity measurement. So inside of a pipe, you've got the circumference of the pipe, but then you've got a rod or a bluff body down the middle of the pipe, also known as a shedder bar. These shedder bars are similar to like a flagpole. If you ever looked outside and you see a flag blowing in the wind, you've got a blunt object or the pole, and you've got a velocity of wind traveling past it. When that wind is blowing fast enough, you get the rippling effect of the flag. A vortex flow meter does the same thing. You've got a pipe, you've got a bluff body in the middle, and then you've got flow traveling past it. That flow traveling past it is going to be measured by a sensor on the backside of that bluff body. That sensor is going to give you a velocity measurement. Saturated steam is commonly used and measured with a vortex meter because of its ability to insert an RTD or a temperature device into that bluff body. When you're measuring steam with a bluff body and the RTD, you're going to get the saturation temperature, which correlates to a pressure in steam. And when you know the pressure, you know what the density of the pressure is or of the steam is, and therefore you're going to get a mass flow measurement. Again, this is a relatively low-cost way of measuring mass flow for steam. This can also be used though for water and for gas. The downside to a vortex is that it has a low flow cutoff that is higher than some of the other measurements. Back to the flagpole analogy, if you've got a flag, a pole, and you've got wind traveling past the pole, the flag lays kind of limp and it's stretched out, but it's not necessarily rippling in the wind. And that's because there's no vortexes being created. Let's go to the thermal mass meter. Inside of the pipe, you've got something that drops down inside. There's 2 RTDs. Those 2 RTDs are side by side, and one measures and one creates heat. The amount of heat loss that's going through there is directly proportional to the amount of mass that is passing past those RTDs. Thermal mass meters are primarily used for gas flow. Often, these thermal mass meters can be used on natural gas or compressed air. some of the most common places that you might see them. Differential pressure is the fifth flow type that we're going to look at today, and it's one of the oldest. Oftentimes, this was used for steam, for air, for liquid, and basically the principle of operation is that you've got a pipe and then you've got some sort of bluff body that's creating a differential pressure from the front side to the back side. You've got two pressure ports that are measuring pressure on the inlet and pressure on the discharge of an orifice plate or of some sort of bluff body that's inside of there. This measurement with known properties such as the gas or the liquid type or the temperatures and pressures, all of these can give you fairly accurate differential flow measurement. One of the downsides to differential pressure flow measurement is that oftentimes you need a lot of straight runs. And straight runs mean if your meter's here and the pipe is coming here, you have to have a lot of straight pipe section before the meter and then straight section after the pipe diameter. The reason that this is necessary is that you need a laminar flow profile or a consistent flow through that pipe. You don't want turbulence rolling through the pipe as it's going past the flow element. If it does, you'll get inaccurate measurement. And again, back to why do we measure flow? We want it to be accurate. We want it to be reliable, and we want it to do its job. These devices are not inexpensive, and we want to buy the right thing for the right job. You don't always use a crescent wrench, you don't always use a box end wrench, but sometimes you need one tool or the other, and that's why there's different types of flow measurements. If you like this information, push the subscribe button, hit the like button, and I'll be back next time with more information about one of these specific meters.